Hey everyone, welcome to this explainer. If you're in grade 9 here in the Philippines studying under the Matatag curriculum, you are in exactly the right place. Today, we're stepping into the fascinating world of physics to unpack one of the most fundamental rules of our entire universe, Newton's second law of motion, which you might also know as the law of acceleration. We are going to break down exactly how and why objects move the way they do. So get ready because you're going to look at the world a little differently after today.
Okay, let's dive right in. Here is our roadmap for today. We'll start with Marco's grocery challenge, then we'll be unpacking the net force, comparing force versus acceleration and mass versus acceleration, before getting into the math of motion, and finally wrapping up with the gravity mind bender.
So, part 1, Marco's grocery challenge. Let's set the scene with an everyday situation that we have literally all experienced, even though it's secretly packed with high-level physics.
Now I want you to think about this for a sec. Why is a full grocery cart so much harder to push than an empty one? Well, picture this. It's a Saturday morning, and Marco is at the grocery store helping his mom. When they first get there, the cart is totally empty, right? He gives it a tiny little push, and whoosh, it just glides down the aisle super quickly and smoothly. He barely has to try to get it to speed up.
But fast forward half an hour, the cart is absolutely loaded. We're talking heavy bags of rice, stacks of canned goods, liters of drinks, the whole shebang. Marco goes to push it again, using the exact same amount of effort he used before. But this time, it barely moves. It is so sluggish. It definitely doesn't speed up like that empty cart did. And Marco is just standing there scratching his head thinking, wait, if I'm pushing just as hard, why is this thing suddenly so stubborn?
Well, when Marco asked his mom about it, she just smiled and said, "That's science." And honestly, she hit the nail on the head. Which brings us perfectly to part 2, unpacking the net force. What Marco was experiencing is actually Newton's second law of motion. Basically, this law tells us that an object accelerates when a net force acts on it. Now that phrase net force is absolutely crucial here. It means there is an unbalanced force acting on the object. Think about it. If you and a friend are pushing a box from opposite sides with the exact same strength, those forces cancel out. They're balanced. The net force is 0, so that box isn't going anywhere. But if you push it all by yourself, boom. Unbalanced force, you've got a net force, and the object accelerates.
Actually, let's pause for a second, because we really need to be precise about what the word acceleration means in physics. In everyday life, we usually just say it when something is speeding up. But in science, acceleration means any change in velocity. So yes, speeding up counts, but so does slowing down, deceleration. And here is the kicker. Even just changing direction counts as acceleration. If an object does any of those 3 things, you can bet 100% there is a net force acting on it. 0 net force simply equals 0 acceleration.
But acceleration doesn't just happen magically on its own. It depends on a few things. Let's look at part 3, force versus acceleration. Imagine a virtual simulation where we have the exact same wooden crate in a few different scenarios. The only thing changing is the push, the applied force. We start by applying a 150 Newton push, then crank it up to 250, then 350, and finally a massive 450 Newtons. The takeaway here is super simple but profound. Applying a bigger net force to the exact same object increases its acceleration. It is literally just like stepping on the gas pedal of a car. The harder you press, the more force the engine makes, and the faster you speed up. And if we take that data and throw it on a graph, look at what we get. A beautiful, straight line shooting right up. In science, this straight line proves that force and acceleration are directly proportional. Meaning, as long as the mass hasn't changed, when force goes up, acceleration goes up at the exact same rate. Bigger push, bigger acceleration. Simple as that. But what if the force stays the same and the object itself changes? Let's get into part 4, mass versus acceleration. So think back to Marco and his grocery cart. Imagine another simulation where a person is pushing with the exact same amount of force every single time. But look at what they're pushing. First, an empty crate, then 2 stacked crates, then a girl sitting on the crates, and finally a full-grown man sitting on them. Just like Marco pushing the empty cart versus the one loaded with heavy rice, applying the exact same push to objects with different masses gives you totally different results. The more mass you add to the equation, the slower the acceleration gets. And this brilliantly shows what we call an inversely proportional relationship. Notice how, as the mass gets higher and higher on the graph, the acceleration drops lower and lower. It creates this sweeping curve known as a hyperbola. So visually, this proves mass and acceleration are inversely proportional. When mass goes up, acceleration goes down. They do the exact opposite.
To really lock this inverse relationship into your brain, let's use a mental image that is highly relatable and, honestly, a little painful. Imagine winding up and kicking a tennis ball as hard as you can. It doesn't have much mass, right? So it flies off, it accelerates incredibly fast. Now imagine taking that exact same full power kick and hitting a heavy bowling ball. Yikes. The bowling ball has way more mass, so with that same force applied, its acceleration is going to be incredibly low, and you are probably walking away with a broken toe. Basically, greater mass fiercely resists acceleration.
All right, so we've visualized it, and we've graphed it. But as grade 9 science students, the real test of mastery here is translating all of this into math. Let's move to part 5, the math of motion. Here is the elegant little formula that ties everything we just talked about together. A equals F net divided by m, or acceleration equals net force divided by mass. In this formula, our force is measured in newtons, mass is in kilograms, and acceleration is in meters per second squared. Oh, and a quick tip, you can easily rearrange this algebraically. Just multiply both sides by mass, and you get the super famous equation, force equals mass times acceleration, or F equals ma. Let's actually put this to work with a sample problem. I'm going to set this up exactly how you'd want to organize it on your test paper. Let's say a net force of 30 newtons acts on a 5-kilogram object. What is its acceleration? We'll break it into 3 sections: given, required, and formula. Our given values are the force, which is 30 newtons, and the mass at 5 kilograms. The required value, the thing we're looking for, is acceleration. And our formula is A equals F divided by m. Setting it up like this is a game changer. You will never get lost halfway through. So let's solve it step by step. Step 1, we write out that formula, A equals F divided by m. Step 2, we plug in the numbers we know. So that's 30 newtons divided by 5 kilograms. And step 3, just do the math. 30 divided by 5 is 6. Now, as for the units, here's a really cool trick to remember. 1 newton is actually just a shortcut for saying 1 kilogram meter per second squared. So when we divide those newtons by kilograms, the kilograms perfectly cancel each other out, and we're left with our beautiful final answer, an acceleration of 6 meters per second squared. Okay, let's see how all this builds into something truly mind-blowing. Welcome to part 6, the gravity mind bender. We're going to apply this exact same math to a scenario that completely baffles most people. But after today, it won't baffle you.
So here is a classic physics trick question for you. Imagine you have a vacuum chamber, meaning a sealed room where all the air resistance has been completely sucked out. If you hold a heavy bowling ball in your right hand and a super light feather in your left, and you drop them at the exact same time, which one hits the ground first? Your gut instinct is probably screaming that the heavy bowling ball has to fall faster, right?
Well, surprise, they fall at the exact same time. They will hit the floor perfectly simultaneously. No way, right? How is that even possible? I mean, the bowling ball is way heavier, so it's definitely being pulled down by a much bigger gravitational force. And didn't we just say a bigger force means a bigger acceleration? We did. But the secret to this trick lies entirely in Newton's second law. Yes, the bowling ball has a much bigger gravitational force pulling it down, but it also has a proportionally bigger mass that is resisting that pull. Remember, mass and weight are directly proportional. When you plug them into our formula, force divided by mass, the ratio stays absolutely constant. Let me show you. A 10-kilogram object has 98 newtons of gravitational force pulling on it. 98 divided by 10 is 9.8 meters per second squared. Now, what about a tiny 1-kilogram object? Well, it only has 9.8 newtons of force on it. 9.8 divided by 1 is still 9.8 meters per second squared. The mathematical ratio is literally identical for the feather and the bowling ball. And that is exactly why every single object in a vacuum falls at the exact same rate.
Which brings us all the way back to Marco and his grocery trip. His mom summed it up perfectly. That's science! What we've seen today is that whether you're struggling to push a grocery cart full of rice, kicking a tennis ball, or dropping a bowling ball in a vacuum, the motion of everything in our universe is governed by this one elegant, unbreakable mathematical relationship. Net force, mass, and acceleration are all linked. So, next time you feel a car speed up or you try to move a heavy piece of furniture, ask yourself, what invisible forces and masses are secretly battling it out to make that happen? Thank you so much for joining me on this Explainer Grade 9. Keep asking questions and keep exploring the amazing science all around you.